Okay, good afternoon. Welcome back. Today we will have our first lecture about the functional programming paradigm. Now, once we talk about the paradigm, we talk about style of programming. And the main objective of the concept of programming languages is to introduce you to different paradigms. And for every paradigm, we will look at the specific programming language. We will take a look at its characteristics and we will try to solve problems using this programming language in this case. Just keep in mind, as a computer scientist, what you have actually to do is, whenever you are having a problem, first of all, you have to think about what will be the best programming language to be used to solve actually this problem. We will have at the end of this course a lecture just to be able to compare the different paradigms and the different programming languages with each other in order to know, okay, when to use what. Now, let me start to go back to the logic programming paradigm. This is actually the paradigm that we looked at before. And in this case, if I have knowledge, if I have a problem that I want to solve, usually you have to solve it in terms of facts and rules. Thus, if I want to perform the addition of two numbers, this is a kind of function that should be implemented. However, in Prolog, okay, what I can implement is a predicate, and this predicate will always return true and false. And that's why I have to simulate functions using predicates. And the way how this can be done is just to define a predicate, okay, that takes three parameters, x, y, z, okay, where the x and the y are, if it would have been a function, are the input actually variables, and the z is the output variable, which corresponds actually to the addition of x plus y. And that's why in Prolog we will read this rule as follows: add of x, y, z holds if the z is the addition of x plus y. Okay. Now, once we have that, and once we compile and we call add of 5, 7, and n, then actually the result will be in this case 12. Okay, now what will happen here is that Prolog will unify this query with the head of the rule. Okay, thus the unification actually works, and then what it does is it just actually resolve the add of 5, 7, and by replacing it by the body of the rule, where the n corresponds actually to the addition of 5 plus 7. Okay, now the main problem, let's say in Prolog, but we saw it before, okay, especially last time once we dealt with the constraint logic programming paradigm. If I want actually to perform the addition of 5 and y and here 15, okay, I should get as a result y is equal to 10. However, here you will be getting an error. Why? Because actually the is operator is a unidirectional operator. It works only if the right hand side, okay, consists of variables that are actually bound in this case. Okay, and that's why what we did last time is to take a look at the constraint logic programming paradigm, which is a kind of an extension of the logic programming paradigm in this case. Thus, we took a look at Prolog. We took Prolog and we enhanced it with constraints. Thus, to use that, we have to load a library which is called CLPFD. Okay, thus it's constraint logic programming over finite domains. And then what we have to do is, instead of writing is, we wrote actually hash equal. Okay, and now once I will compile, okay, what will happen in this case here, okay, if I will perform the addition of 5, 7, and you get actually as a result n equal to 12, which is identical to what Prolog actually gave me. And now what I want actually to do is, I want actually to get now a result, okay, which is a binding for the y that will satisfy add 5, y, and 15. And here you get a nice result, because actually this hash equal will be considered to be a constraint. I will be having an equation. The equation is having one single unknown, okay, one single variable which is unknown, and this can be actually determined, because here I will be having 15 is equal to x plus y, where the x is equal to 5 plus y. That's actually automatically you can deduce that the y has to be equal to 10 in this case. Okay, now this is in a nutshell what we did in logic programming. This is what we did in Prolog, and then you have actually to know if I am having a problem and the problem let's say has more than one solution, then in this case I can backtrack in this case. Okay, I will give you an example. If I am having male Ali, okay, and male Ahmed, okay, and male Mina, okay, what I can do here is the following. I can ask about, let's say, whether Mina is male or not, and then you get as a result, yes, he is male. And now if you want actually to ask how I could satisfy male of L, then in this case what will happen in Prolog, that unification will be performed. That means L will be equal to Ali, and if L is equal to Ali, then male of L is true. And this is actually the first result that you get. And now what I can do is I can trigger backtracking, okay, in order to get, let's say, alternative solutions in this case. And if I will do it, then Prolog will tell me, yes, I can also unify male of L with male of Ahmed, where the L will be equal to Ahmed, and the result here in this case, if L is equal to Ahmed, then male of L is true. And last but not least, if I will ask about alternatives, I get actually the following, that male of L can be unified with male of Mina, and that's why in this case the L will be equal to Mina, and if L is equal to Mina, then male of L will be true in this case. Okay, this is actually Prolog. Prolog actually is based on, let's say, different concepts. One of them is unification, the second one is resolution, and last but not least is backtracking. Okay, the unification is just to know which rule or which fact I will use just to be able to resolve my problem. Resolution is just to change the query, to replace the query by the body of the rule if there is any. Okay, and last but not least, backtracking is there in order actually to find alternative solutions if there are alternative solutions in this case. Okay, now let me go to functional programming. Okay, in functional programming, everything is based on functions. That means actually the whole computation is mainly based on evaluation of functions. Okay, and that's why we talk about, let's say, an expression-oriented programming language. And here, like in Prolog, we will be actually expressing the what, and we will not care about the how. The what is my problem, and the how is how will the machine execute, let's say, the program in order actually to get a solution. We won't actually care a lot about it. However, you will see exactly later how the evaluation will be done in order to understand how the programming language or a functional programming language works. There are different actually programming languages in the functional programming paradigm. Okay. The first language is Scheme, okay, was introduced actually in, let's say, in the AI era. Okay, then actually we had Lisp as a kind of dialect for this programming language, and the last, let's say, programming languages that were introduced 20, 30 years ago, they were Haskell, Scala, or Camel in this case. Now, in this course, we will be focusing on the functional programming paradigm, okay, and we will just actually start to see actually how we will be able actually to work with Haskell. Okay, thus to work with Haskell, we need either a compiler or an interpreter. Okay, thus we will be using Hux. Okay. There are different versions. We'll be using here actually Hux in this case, and you will see exactly how the whole thing will work. Okay, I will show you now. Let's say this is WinHux. Okay, now I have a kind of an interpreter, and the interpreter can perform, let's say, an evaluation of any expression. That means if I will write 9, then actually the result will be 9, because actually 9 is an expression. If I will write 9 plus 33, then I will be performing the addition of two numbers. Then in this case the result should be 42, and you get actually 42 as a result. Okay, thus if I write an expression of the following form, 9 plus 3 minus let's say 6, okay, then the plus and the 6 are having the same precedence, and that's why the evaluation will be done from the left to the right. Thus 9 plus 3 will be equal to 12, 12 minus 6 will be equal to 6, and this is the result that you will be getting here. Okay, now please take care. If I will write something of the following form, okay, 9 plus x, the first thing that you have to think of is whether you will be able actually to evaluate it, okay, because actually the whole thing, the whole interpreter is based on a kind of execution of functions. In this case here I'm talking about operators. Thus 9 plus x, you will tell me, but I don't have actually the value of x, and this is exactly what Haskell, the Haskell interpreter will tell me. It will tell me, I'm sorry, I really do not have any variable which is actually defined, okay, for x, and that's why I don't have a value for it, and that's why I cannot evaluate the expression 9 plus x. Okay, now please look what I will do. Okay, once I will open Hux, automatically the prelude, which is a library, will be loaded automatically in the interpreter itself. And that's why if I want actually to ask about whether 9 is an even number, you should get actually false. You get actually false. That's the even is defined. If I will be having even of 90, 90 is an even number, and then what you will get here as a result is true. Okay, now let's move on, and let's start actually with the first problem that we want actually to solve. Yes, I'm having here a notepad. Okay, and what I will do is I will be implementing my program here, and in the interpreter I will load it. Okay, and last but not least, I will just try actually to execute some expressions in this case. Okay, I will start with the following one. Okay, everything is based on expressions. I will start actually to do it like we were writing expressions in math. Thus, if I take actually two parameters, x and y, okay, then I will be performing the addition of x plus y. This one actually is equal to x plus y. Okay, now I will just actually save, and then last but not least I will go here and I will load it actually for the first time. Haskell. Okay, thus in this case the whole file actually will be loaded, and then what I can do is I can actually perform the addition of 6 and 7. Okay, what I'm doing here is I am actually performing now a kind of an execution of a function. That's an addition of 6, 7. Okay, there is a function symbol called add. Okay, and in this case 6 plus 7 should give me 13, and you get actually here a small problem. Okay, why? Because actually you don't need actually to write actually the dot, and that's why once you will do it with add 6, 7 here, you will see that you will get confused. I did it actually on purpose. Okay, since in Prolog you were always writing something actually where you will terminate it with the dot. Here I'm actually talking about expressions. There are actually no dots. That means everything that you will write is about expression evaluation in this case. Okay, now if I have the addition of 4, 3, okay, then this one actually could work, and the question is it possible to write something of the following form: add of 4 and add of 3 and 5? Okay, I will tell you for sure it will work, because actually if I have the add of 3, 5, the result will be 8, and if I have the addition of 4 and 8, this one actually should work, and the result will be equal to 12. Okay, thus if I have actually to multiply, okay, let's say x and y, now in this case what will happen here is I will be having as a result x times y. Okay, thus once we have that, once we go here we will load, and the load actually will be done with the column r. Okay, thus the question is it possible to add, let's say 3, okay, and let's say add it to the result of multiplying 2 and 4. Okay, thus 2 multiplied 4 will be equal to 8. 8 plus 3 should be equal to 11, and you get as a result 11. And here you see that actually you will be performing a kind of an evaluation of expressions in this case. Okay, now let's take a look at this function. Okay, you will see it actually more whenever actually we are dealing with the data types of the functions in this case, because here you see that actually I'm not defining any data type for the variables. However, what Haskell will do is will infer automatically the data type in this case. Okay, thus please keep in mind this is actually what we write in math. I will change it actually slightly. Now I will be removing the brackets, and you have actually to get used to that. And once you want to perform, let's say, to write a function at, then you will write at xy. Once you want actually to perform the multiplication of two numbers, you will write it actually as multiply xy. Now this is actually something which is called the curried form of a function. Okay, and most of let's say the functions, if not all, they have actually to be implemented in a curried way, and there is a reason why. Okay, now once I will go and I will load, okay, the whole thing actually will work. However, once I will perform now the addition of 4 and 5, you have to do it actually in this way. That's without writing actually brackets, because if you will write bracket, okay, what will happen in this case, you get a problem, because Haskell will tell you, I'm sorry, I was trying actually to find a function that takes a pair as an input. I don't actually find it, and that's why I will be telling you that I cannot infer, let's say, the instance of the function in this case. Okay, now the question is, if I want actually to add 4, okay, and then add it actually to the addition of 3 and 1, okay, the interpreter, the Hux interpreter, will tell you it's a simple task. Add 3 and 1 will give me 4. 4 plus 4 should give me 8, and you get actually 8 as a result. And that's why you can for sure, let's say, combine things actually with each other. You will be performing the addition of 3 and 4, okay, and you will be just multiplying 3 with 4. Okay, thus the question is, what will happen? Add 3 4 will give me 7. Okay, multiply 3 4 will give me 12. 12 actually plus 7 will give me 19, and you get actually the result correctly in this case. Okay, now please take a look at the function. Okay, take a look at what I am actually writing. Okay, and the question is it possible to perform the addition of, let's say, CSEN, okay, and hello? Okay, we will just write out, keeping in mind that let's say similar actually to Java, okay, a string will be written between double quotes. Okay, however, the Haskell interpreter will tell you, I'm sorry, I'm having a problem. Okay, the addition cannot be used actually to perform a kind of an addition or a concatenation of two strings. Okay, now just actually keep in mind that the programming language is typed. Next week we will be having actually a kind of lecture about typing. However, let me give you an idea about it. Now actually, if I write :T, okay, now the 4 or :T means actually the type of 4. Now just actually keep in mind that the 4 could be let's say considered to be either an integer or a kind of floating point number. Okay, and that's why what you get here is it tells you the 4 is of type A, where A is a numeric value. Okay, now once I will go and I will write here 4.3, I will know exactly it's not any numeric value, because an integer is a numeric value, a floating point number is a numeric value, but 4.3 is a fractional value. That means it tells you it's of type A, where actually the A is of a fractional type. Okay, now if I will write here :T and then CSEN, okay, what you will get here is it tells you, okay, the CSEN is of type string. Okay, now if you write something of the following form, type of 1 2 3 4, keeping in mind that 1 2 3 4 is a list, it tells you, okay, the 1 2 3 4 is a list of A's where the A's are of a numeric value. Just keep in mind, okay, Haskell is a typed programming language, and the typing will be inferred automatically by Haskell. Okay, now the question is, okay, this is nice, this is actually a function. Once actually I will call it, you will be having let's say a way how to call it in the interpreter. Okay, thus if I will have a successor of x, then the successor of x is equal to x plus 1. Okay, thus now once I will load, I will know exactly that there is a function called successor. I will call it actually with successor of 77, and the result will be equal to 78 in this case. Okay, now the question is, what if I want actually here in the interpreter to perform the evaluation of a specific expression without actually having a name for it? Okay, now I will show you something called anonymous functions. This is actually the way how we will do it. You will write something called a lambda expression. Okay, now the lambda expressions is the A and the O for the function programming actually paradigm, and the lambda calculus is actually the calculus that defines how functions are defined correctly in math, as well as how they are actually evaluated in this case. Now how will I do it? I want actually to define let's say a lambda expression that depends on x. Okay, I will do it with dash and then greater, and then I will perform, let's say, the addition of x plus 1. This is actually the expression, and then I will write 66, meaning I want actually to evaluate this expression actually with the value 66, and the result should be equal to 67, and you get as a result 67. Okay, now the question is it possible to write a lambda expression that depends on more than one variable? I will tell you yes. You can do it as follows: backslash x y, okay, without any let's say delimiter between the two variables, and then I will be writing x plus y. Okay, now I know exactly that this expression expects actually two values. I will write 99 and 22. The result should be 121, and what you get here is you will be getting 121. Okay, thus what I am writing here is a function. Okay, it's a lambda expression. Okay, here it depends on only one variable, and this is the expression, this is the body of, let's say, the function in this case. But it's anonymous because once I define it, I cannot, let's say, call it by its name because I don't have a name for it, and that's why, okay, these type of functions will be called in this case anonymous functions. Okay, now and let's move on. And what I want actually to do is I want actually to calculate an absolute value of a number x. Okay, now in this case you will need actually to know the constructs that are defined in the programming language. Okay, now the first construct is the if then else. Okay, thus I will write something of the following form: if x greater than or equal to 0, then in this case the result should be x, else the result should be minus x. Okay, thus once I will go and once I will load, let's see what will happen. Okay, it tells you, okay, the file actually looks nice, there are actually no errors, and that's why once I will have an absolute of 9, okay, the absolute of 9 should be equal to 9, and you get actually 9 as a result. And now once I want actually to have an absolute of minus 1, you have to take care. Here you will be getting an error. Okay, why? Because what Haskell will do is it will seal absolute of minus and then actually 1. Thus it doesn't actually take this one as a number. In order to consider the whole thing as a number, you have actually to put it between parentheses in this case. Thus, an absolute of -1 will give you in this case 1. An absolute of 0 should give me in this case 0 as a result, and you get actually 0 as a result. That means the absolute value actually will work. Okay, now the question is it possible to write a kind of an if-then without an else? Okay, I will just actually remove it. Okay, and I will try to load it. Okay, and what you will get here is you will be getting a problem. It tells you, I'm sorry, absolute x is equal to, if x is greater than 0, then x. I'm sorry, you need actually to have always an else part. In this case, it's not like Prolog, it's not like Java, it's not like Python. Okay, the programming language, whenever you use an if-then, then actually else is a mandatory one. And that's why there is no dangling problem in this case, because actually you know exactly if I am having an if, okay, then there will be actually two parts. One part is the then and the other part is the else part. Okay, that's, I will go here. Okay, and what I will do, I will save it, I will go back and I will reload actually the file. The file works, and now you can actually do it with absolute of 22, and this one will work. Okay, this is actually one way how you can implement an absolute value. There is another way how this can be done, which is actually something called guarded expressions. Okay, you will write something of the following form. Absolute 2 of x is equal to, okay, and now you will write actually a condition. If x is greater than 0, then in this case I will be having x as a result. Okay, now let's actually go, let's load. Okay, then you will be having actually a problem in this case. Okay, why? Because what I am having here is just an equality, and the guarded actually expression will not work. Okay, now to do that, what you need actually to do is you need actually to define it as follows. Okay, the guard will be equal here. Okay, and it tells you if x is greater than 0, then the whole thing will be equal to x in this case. This is actually the guard. Now once you will load, this one actually will load. Once you talk about the absolute value of 99, you get as a result 99. Okay, however, now once I will be having absolute of 2 of minus 22, okay, now you will see that actually there is an error because there is no case actually that will cover this one. Okay, now the question is how can I do it? I will just actually write the following. Okay, otherwise the whole thing will be equal to minus x. Okay, thus in this case, once you will load, okay, you call an absolute 2 of 99, you get 99 as a result. Okay, now you go and you get actually absolute 2 of minus 22, and what you get as a result in this case is 22. Okay, thus this is actually something which is, okay, absolute value implemented with an if then else, and this is an absolute value which is implemented using a guarded expression in this case. Okay, now let's go further and let's see how recursive methods can be implemented. It's a function, the thing, okay, that you implement in that you write actually in math. Okay, you have actually to find a way how to write it either with if then else statements or with guarded equations or with something else that you will see in few minutes. Okay, thus I will go actually to the factorial of x. Okay, now what I will do is I will just actually define it, and in order to do it actually in a carried way, I will write factorial x without using any brackets. Just actually keep in mind, to the left hand side you do not actually write the arguments between brackets, and you do not actually separate them with commas. Okay, and that's why what I will do is I will do the following. Wallahi, if x is equal to 0, then in this case my value will be 1. It's about expression. Okay, else what I will do is I will write x times and then factorial of x minus 1. Okay, thus in this case what will happen here is I will be having a factorial of x if x is equal to 0, then 1, else x times factorial of x minus 1. Now I will go, I will load, and what I will do is I will just actually call the factorial of 5. Okay, factorial of 5 should give me 120 as a result, and you get 120. Factorial of 7 should give me 5040, and it gives me 5040. And then I think is if you do it actually with the number, okay, which is a big one, you get it. If you do it actually with 700, you get actually a huge number, and if you do it actually with 7000, then actually the number that will be calculated will be a huge one. Why? Because actually the data type of numeric values of integers is an unlimited one. That means the problem that we are having in Java, where an integer could be of let's say data type int with 32 bits, that means the largest number will be 2 to the power of 31 minus 1. Or if I go too long, then actually you are having 64 bits, then the largest number will be represented as 2 to the power of 63 minus 1. This problem will not occur here, because actually the data type, the range of it, the total number of bits that will be reserved is an unlimited one. Okay, this is actually one way how the factorial actually can be implemented. Okay, now I will go and implement actually factorial 2 with guarded expressions. Okay, that's factorial 2 of x. Okay, and I will write the following bar. Okay, that gives me actually the guard x equal to 0. In this case, the whole expression will be equal to 1. Okay, and then I will go, let's say down, and I will write in this case otherwise. Okay, I will be writing in this case equal to, and then x times factorial 2 of x minus 1. Okay, and now let's see how the whole thing will work. I will go, I will load, I will call it factorial 2 of 9. Okay, and this one actually will work. It will give me a result. I will do it with 0. This one actually will give me 1. And if I will do it with a negative number, okay, what will happen in this case, it gives you actually as a result that, I'm sorry, it's minus 1 between brackets. Okay, it gives you a stack overflow, because actually the whole thing will never will never actually terminate, because actually here the anchor case is with the 0, okay, where the value will be equal to 1, and this one actually will go always actually to numbers that are smaller than minus 1. You get to minus 2, minus 3, minus 4, and this will never actually reach the anchor case in this case. Okay, now I will just actually tell you the best way how you can implement, let's say, functions, okay, without writing them neither with if then else statements nor with guarded expressions. Thus, this is actually, let's say, the comment in Prolog. This is an if then else statement. Okay, now this one will be something called guarded equations. Okay, and the guard is just the condition. That means here you read it as follows: factorial 2 of x. If x is equal to 0 is equal to 1, otherwise is equal to x times factorial 2 of x minus 1. And last but not least, I will write here pattern matching. Okay, now it will look actually similar to the way how we will be implementing functions, or we will be writing actually functions in math. Thus, el factorial 3 of 0 is equal to 1. Okay, this is actually the first, let's say, match. Factorial 3 of x, okay, is equal to x times, okay, factorial 3 of x minus 1. Now, once you will do it, if you will go here and you will load, okay, and you call the factorial 3 of 5, you will be getting as a result 120. Okay, if you write factorial 3 of 0, then actually you get 1. Now, because here I will be seeing actually something that will matches actually this pattern, and you will get as a result here equal to 1 if you call it with factorial 3 of 0. If you call it actually with factorial 3 of 5, okay, this doesn't actually match the first pattern, but it matches actually the second one. And then what I will do is I will replace factorial 3 of 5 by 5 times factorial 3 of 4. Then the factorial 3 of 4 will be replaced by 4 times factorial 3 of 3, and so on. That means this one actually will go over and over again till I reach actually the last call with factorial 3 of 0, and this one will give me as a result, let's say, the value or the value of multiplying 5 times 4 times 3 times 2 times 1 in this case. Okay, now let's see whether the order of the expression will change. Okay, now once you will do it, if I will do it like that, and I will load, this one actually will load correctly. And now once I will go actually to factorial 3 of 5, the order actually will be crucial in this case, and you get actually a stack overflow. Why? Because what will happen here is I will be getting, let's say, the values one by one, okay, and what will happen, I will get actually the factorial 3 of 5, and I will match it actually with this first pattern. It does actually match, and that's why I will neglect actually the last one. Thus you go and you multiply, in this case 5 times factorial 3 of 4, and so on. And that's why you will see it here. If you call factorial 3 of 0, okay, then this one actually will go directly actually into an infinite actually loop, and the factorial 0 of 1 will never be reached in this case. And that's why, first of all, the order is crucial. Okay, thus I will go here, I will load, and I will call it actually factorial 3 of 0. This one will work. If I will call it with factorial 3 of 5, this one actually will work. Why? Because actually the pattern will match, okay, for the second one, but not for the first one if you call it with factorial 3 of 5. And this one will be just an expression that will be evaluated. That means this expression will be replaced by 5 times factorial 3 of 4. This one is a recursive call that will call the method or the function over and over again till you get actually a result in this case. Okay, and please actually keep in mind what we were able to do in Prolog, where you defined actually something of the following form: factorial 3 of x. Okay, I will tell you, can you evaluate an expression which is a function, okay, and it's defined actually with an x, and the x for you will be considered to be, in this case, a variable. Okay, now Prolog does actually unify, but in this case, in a functional programming paradigm, we do not actually unify, but what we do is we evaluate expressions. This x doesn't have actually a value, and that's why what will happen in this case, okay, Haskell will tell you, I'm having a problem, I have never seen actually something defined actually for x. Okay, now you see that the x is written actually uppercase. It will be considered to be a constructor. You will see that the next lecture whenever we talk about actually data types in this case. Now if I will write factorial 3 of x, the same problem actually will occur, but it tells you undefined variable in this case, because actually the x is written in lower case. Now look, if I will go here and I will write x is equal to 5, now I'm defining it. Okay, now once I will go here and I will load, okay, what you will get here is whenever I talk factorial 3 of x, the x actually is already bound, it's equal to 5. That means I will be computing el factorial 3 of 5, which will give me actually 120. Okay, now hope the lecture is clear. The lecture is an easy one. Okay, thus we were actually talking about different ways how you implement if then else statements. Okay, either the classical, let's say, if then else statements, where actually the else has to be always there. That means it cannot be actually written as an optional one. Then we took a look at guarded expressions in order actually to let's say write something that doesn't have an else part. You can actually in this case write it with a guarded expression. There is no need actually to have an otherwise part if you don't want actually to have it. And last but not least, we looked at an example where we were actually dealing with pattern matching rather than guarded equations nor if then else statements in this case. Okay. The lecture is simple, it's easy. The functional programming paradigm is let's say one of the paradigms that is used a lot actually even in industry. We will be looking at the end of the semester a lecture that introduces where functional programming paradigm is used in the industry in this case. Okay, thank you very much for watching, and see you inshallah next time with having actually more example about let's say types. I will just actually show you one example. If I want actually to know the data type of even, it tells you the A is of type integral. Okay, you will see exactly what the class actually integral is. Okay, and what it returns here is it returns actually a Boolean value in this case. Okay, and here this is actually how you are defining functions, or how the function is defined, and how the inference machine for the type will infer actually the data type for functions automatically in this case. Okay, thank you very much for watching, and see you soon. Assalamu alaikum, and have fun. Bye bye. Take care.